So good morning, everyone, and welcome to this edition of our monthly meetups organized by CLIQ-ai, the Computational Linguistics in Quebec Consortium. My name is Fabricio Gotti. I'm a programmer specialized in NLP. I'm working at the University of Montreal and for Ivado. So once again, today we have three very interesting talks, including a demo, the last one, revolving around the topic of graph neural networks in natural language processing. We're going to have a presentation by Lingfei Wu, who works at JD.com, entitled Deep Learning on Graphs for NLP. Then a presentation by Bang Liu, who's professor at the University of Montreal at RALI, who's going to talk about graph representation and learning for hot events tracking and user interests modeling. And finally, we're going to have a presentation and a demo by Hugo Chen, who's a research scientist at Facebook AI. So before we start, I'll ask everyone to turn off your cameras and mute yourselves so that we can enjoy the presentations distraction-free and to save on bandwidth. So every talk is going to be followed by a 5 to 10 minute question and answer session. So you can write down your questions as the presentation unfolds, so you can ask them at the end of each presentation. If you want, you can ask the question in French, and we're going to translate it for our speaker. So let's move on now to the first presentation by Lingfei Wu, who's going to present deep learning on graphs for natural language processing. Dr. Lingfei Wu is a renowned scientist and currently a principal scientist at JD.com Silicon Valley Research Center. He leads a team of more than 30 machine learning, natural language processing, and recommendation system scientists and software engineers to build the next generation of intelligent e-commerce systems at JD.com. JD.com is a very large e-commerce solution in China. He has published more than 90 top-ranked conference papers, and he's the co-inventor of more than 40 US patents. So without further ado, I'm going to ask Dr. Wu to share his screen if it's possible.
Thank you for the introduction. Let me share screen now.
Yes. Very good.
Interesting. I just put the Microsoft Teams as a permission, but since it's ask me to do that again. Let me see. Can you guys see my screen now or not?
Yes, we can see your screen.
Okay, perfect. Okay.
So you can start the presentation if you want, because perfect, exactly.
Okay. Okay, first of all, so thank you so much for the invitation and for the nice introduction. So my name is Lingfei Wu. So currently I'm a principal scientist at JD.com. So JD.com is the largest returner in e-commerce returner in China, just like Amazon in US. So just give you some idea. So how large is the JD.com? So in American, we have a Thanksgiving Black Friday, right? Everyone knows that. So in China, so we don't have Thanksgiving, but we have invented two different holiday. One is in June 18th. It's JD, kind of like JD shopping happy day, and 11/11. That's November 11. Just last week. So that is also a very large shopping happy day. So on that day, like every big e-commerce company in China will participate in that, and we'll try to hit a record for a total number of the selling items. And JD.com is on that day, we have hit the record high GMV this year. We have a total sold more than 50 billion 50 billion goods on that day. So this is really impressive. So that's mean how many people in China, so they're really enjoying shopping on that day. So just give you a rough number about so how large is the JD.com business. So today I'm going to talk about the deep learning on graph for natural language processing. So this is my favorite topic in the recent several years. So we have 3 different topics here: deep learning, graphs, and natural language processing. So you maybe already heard about deep learning, you might heard about a graph and then NLP, but put them together, we have also very exciting topic here. So so this is also a joint work with our graph for NLP team. So can you guys see the blinker screen in the surround of the slides, or just my screen like this?
No, we see your screen. It's perfect.
Oh, okay.
There is no blinking.
Oh, okay, good, okay. So this is outline for this basically shorter version of our tutorial. Okay, we have been giving tutorial last year. Actually not last year, this year in LACO, in KDD, in EJICA, and CLIQ-ai. So we have been trying to advocate this topic. So so deep learning graph and NLP is not really some new area. Okay, so because conventionally in the last 2 decades, there have been intensive research have been working on how to using graph for NLP. And so then we are talking about a little bit what's the conventional machine learning technique for various NLP tasks. And we were moving to the model era, and with the rising of the deep learning. So what kind of deep learning on graph technique that we can leverage to solve various NLP tasks. And in the second part, so I will focus on the 2 things. One is graph construction, means that once we have a text sequence, so how can we construct a graph so that we can use that to fit to the graph representation learning technique later to run a meaningful representation and powerful representation for the various NLP tasks. The second part will be, once you have a construct graph at hand, so what kind of a graph representation learning technique should we use when graph, for example, is a homogeneous graph, or it's a multi-directional graph, or it's a heterogeneous graph? And then I will talk about a little bit of the future direction of this part. And so down or later, we'll talk about the various application with a deep learning graph, and also you will talk about our recent release library, graph and NLP library, and talk about some demos and how to use this library. Okay, so first part, so why we care about graph? That's really because that graph is a generic language that can be used to describing and model the complex system. Just showing the right-hand side, right? So the graph is very simple, the structure. So you have a bunch of the graph nodes that represents any object, and you have an edge that represents the relationship or the similarity between 2 graph nodes. And just give a concrete example here. So everyone knows that today everyone is connected in the social media, YouTube, almost every online app you are aware of is essentially in the database. You may connect as a graph, and just put like a search engine as example. So when you try to query something or try to buy something, right? So it's the system try to give you the personalized result based on the either recommendation or the search system. And so you can see that. So when we talk about the deep learning graph, we really talk about 2 things. One is the graph topology, that's the connectivity information that formulated by all kind of users and items. Okay, and also for each of the graph node, it will associate with graph attributes. So this is essentially very important information for the algorithm to start. Of course, it depends on what kind of downstream task we try to tackle. you maybe want to do the node classification task or graph level classification task or link prediction. So the node type is another one, the information that later you are going to predict if you are trying to do the node classification task. So graph data is everywhere. Just as I mentioned, ranging from the internet to the social network is very natural. And in the information retrieval system today, more and more people pay attention to the graph structure because it really can leverage a lot of different data information together. And in the this recently people have been paying a lot of attention to the AI drug discovery that essentially try to model the chemical compound as a graph and then try to discover the new drug, for example. And even in the program synthetic area, people try to leverage the controlled flow graph or data flow graph, try to do the program analysis. In computer vision, people using a scene graph to do the high-level reasoning over image. So in NLP, it's more natural because in NLP, the human language is not a simple sequence. The human language is high-level symbol. So there's a lot of the hidden structure behind the text sequence that we have seen so far. So that depends on what kind of a direction that we'll try to take a look. For example, if we look at in the syntactic level, so we can use variants of the depends path tree tool to analyze your current text sequence, get the sentence structure. For example, the depends path tree or constitution tree, so that it will give a different level of the sentence structure information. This is the syntactic information. But if you want to know the semantic information, you can also use other tool. For example, you can use the MR parser to get an MR graph that you can represent a sentence that in the semantic meaning level. And also you can use the OpenIE tool, for example, to get the information graph so that you can extract the key triplet about each of the sentence or even a paragraph so that you can get more condensed information from this text sequence. For some applications, right, so like SQL, the SQL sequence essentially, it looks like sequence, but not really, right? Because different clauses don't really have all the information. Therefore, that you can, it's better to construct a graph instead of using sequence to represent this. So this is more like an application-driven approach to construct a graph. But this is very important because once you have a domain knowledge, it definitely makes sense to think about the relationship between different entities and then try to augment kind of sequence in order to get the additional information. So, so with this in hand, so now we know that it's very natural to think about graphs in the NLP domain because everything's really is more complicated than its original text sequence. So there are already many machine learning techniques have been proposed when we try to use a machine learning on graph for NLP. But first, let's take a look. So how do we represent a natural language, step by step over the last 2 decades? So just I'll show you the right-hand side, right? So we have a bunch of the sentences here. So originally, so when people try to think about the natural language, it's more like, they disregarded any kind of semantic meaning. They just treat it as kind of like a bag of tokens or symbols. And then they just simply use like a backward or TF-IDF type of approach, try to represent a sentence or document as a sparse vector representation. But later people, especially with the rising of the word-to-vector technique, and everyone must be aware of that very well, starting from the 2014. So people realize that so when we transform the original token into the dense space in the latent space, we found that a dense vector is a much better representation to preserve the original semantic meaning in this case. So therefore people later completely change the NLP foundation. People try to represent the natural language as a sequence of the token now, and then using like a word vector, growth vector, or conditional field to solve the problem. And so of course, more recently, right, people tend to go to the pre-trained language model. Right now, we try to use a contextualized word representation, try to generate a more accurate word representation in specific for the current task. So this is definitely a new trending and also new foundation for the most of the NLP tasks today. So as I mentioned before, so it's very natural to represent the natural language as a graph. So as I mentioned before, like dependent class tree, confusion tree, MR graph, all so on and so forth. So this is definitely one way to try to generate a graph based on the kind of text sequence. But even for the most simple one, for example, a text graph, if this is simple, think about it as a paragraph, right? There is constituted by a multiple sentence. Each sentence is constituted by a multiple word. So it's very natural to construct a hierarchical element of the graph to formulate a text graph that is composed by the document, sentence, and the word, just I show you on the right-hand side. So there have a lot of the algorithm have been proposed. Of course, most of the algorithm here I'm talking about is more conventional machine learning technique. So here I just pick 4 representative algorithms that have been used extensively in the literature and applications to solve the real applications. So for example, people have been using random walk algorithm that essentially try to generate a random path, try to get a standard distribution of the old graph node. This once it gets the representation, you can use that to do semantic similarity of text, or you can do the lemma disambiguation task. And people also can be formulate this text clustering problem as a graph clustering problem, and then you can leverage like the spectrum clustering, this type of the algorithm to solve the problem. People also have been trying to using graph matching algorithm for the text entailment problem, which is try to compute the similarity between 2 sentences. So once you can represent the 2 sentences as the 2 graphs, then you can use graph matching algorithm to do that. People have been also using a label propagation algorithm, try to propagate the label of the labels of the label of data point to the previous ANSI data point, so that you can generate a representation for each of the data point, and then later to use that representation to do the word sensitive ambiguation and sentiment analysis task. So for more information about the conventional one, I will refer to the Mahase and Radev a book, a graph-based method for the lecture language processing and information retrieval, published in the 2010 by the Cambridge. So now it's time to talk about the deep learning on graph. Okay, so this is the most important part. We want the basic foundation we want to talk about, but there are many techniques that have been using deep learning on graph. So the most early one probably is like networking embedding. That once you have a networking topology, you can generate a representation for each of the graph node, so that later you can use that representation to do any task. But when we talk about deep learning today, I will mainly focus on the graph neural nets, because this is a more recent advanced deep learning approach on graph, and have been demonstrated as a very powerful technique for the variance of the tasks. So you must be very familiar with this machine learning life cycle, right? So as we know that, so the feature representation is the most important part. So traditionally, before the deep learning, people spend a lot of time to do the feature engineering in order to get a better, to transform, to get a better feature matrix. That's what we'll talk about today, transform from the raw data. But with the right deep learning, we right now tend to use a neural net to try to automatically learn the feature from the raw data to the structured data, so that later we feed it to any learning algorithm and to learn the model. So with this same concept in mind, so the feature learning in graph is a similar thing. So our goal is still try to design an efficient task-independent or task-dependent feature learning algorithm in order to transform the graph node into its latent space, so that we can use a vector representation to represent the current graph node and then to do any downstream task. So the graph neural nets essentially is the first paper published in 2016 by Jali from DeepMind. So that paper essentially is called Gated Graph Neural Nets. It's really the first modern paper in the graph neural domain. So later, Thomas Kipper also invent another most popular graph neural variant called graph convolutional neural. That essentially is, I think it's a milestone for the graph neural domain because that paper is the method is so simple to use. So really later boosts the whole area. So when we talk about the graph neurals, essentially, right, it's a type of the machine learning algorithm that try to learn a graph node representation based on the two input. One is graph topology, other one is the node attribute. So you can see that it's very important to define graph filtering. And the graph filtering process, it tries to take the graph adjacent matrix A and the node attribute H as an input, and then transform to aggregate the information from the graph, and then try to update the node representation for the next iteration. Based on the type of the graph filtering, you can generally divide them into the 4 different categories: spectrum-based method, spatial-based method, attention-based method, and recurrent-based method. So, however, the graph filtering process don't really change the graph structure. So therefore, that if you want to learn a graph level representation, you have to use a different operation. So here we introduce a graph pooling operation. Essentially, you try to take the input graph and input the node embedding as an input, and then to generate a smaller graph with a fewer node, and then corresponding node representation. So there are 2 different types of the graph pooling operation: the flat graph pooling and hierarchical graph pooling. The flat graph pooling is fairly easy to understand. Once you have a node representation for each of the graph node, you can use mass pooling or average pooling or mean pooling to generate a single vector that to summarize the whole graph, right? So this is probably the most used operation when we try to get the graph level representation in NLP domain. But however, in general graph neural domain, so we have a most advanced algorithm, for example, using hierarchical graph pooling that essentially try to using coupling operation to generate each layer of the graph with a smaller graph, and then later to using the representation for each of the layer to generate the final graph level representation, and showing that they have a better performance. But in NLP applications, I would say the flat graph pooling probably is already enough. So before I go to this slide, so from this slide to later, like about 7 or 8 slides, it's basically about kind of like a basic model or basic example to showing how graph neurons works. But I don't know, what's the foundation of our audience. So if anyone is already quite familiar with, basic graph neurons concept, then I will skip these slides. But if you are not, I will go through this slide.
Please go ahead with this slide.
Okay. So this is, basically the key idea of the graph neurons, right? Is try to generate a node representation based on the local neighborhood. Just give example, right? So you have an input graph A here, and in order to learn the representation of A, you just basically learn the context information, right? So what's the context information for A? Essentially, the most important one probably is the first order neighborhood, like B, C, D, and correspondingly, the graph node B also have a neighborhood N, C, right? So then we can formulate this unique graph computation graph. And similarly, right, so then the whole graph can define a unique computation graph for each of the graph node. And then, we can do this neighborhood aggregation here. So for example, in the layer 0, right, at the very beginning, so each of the graph node will have its own node attribute. And this is very important because, once you have this real world information, you should put that information attach it to each graph node. This is more like a feature matrix that we talked about before for each of the graph node, for each of the data sample, but here is graph node. Okay, and then you transform the latent space and then try to do the aggregation. And this conceptually, the depth of this graph nodes could be arbitrary, but in reality, it's not. In reality, right, it really depends on the kind of the graph nodes you are using. So, typically it cannot go that far. Otherwise, you will have over smoothing problem. So, for example, for the well-known GCN, typically use only 2 or 3 layers. If you really use 5 layers or more than that, so you will get a very bad result. That's over 50. So that is a very active, another very active research topic in the graph neural domain. So once you get the information, so you basically try to propagate the message through the graph, and then you will get the representation for each of the graph node. So now let's take a look at the overall, computer flow. So you first define a neighborhood aggregation function, including anyone, and then try to aggregate the information from your first order neighborhood to this to your current node. and then you will do the second propagation, so that you can propagate information through the whole network, and then to generate a graph representation for each of the graph node. And then you can define a loss function on the representation so that you can do any downstream task. So the good thing, so you can train that on the set of the node, such as the batch of the compute graph that, as we mentioned before, right? Each of the graph nodes have a unique computation graph. And then the most interesting part of that, so because since we learn the aggregation function instead of the parameter for each of the graph nodes, so essentially it's inductive learning, right? So even though for the graph node, graph node you never seen before, assuming that the graph is evolving over time. So around that you have already learned the graph aggregation function, you can easily to compute the graph representation based on the neighborhood embedding, and also the learned parameter. So just a very simple example, if you neighborhood aggregation function is the average function, then just simply apply the average message from neighborhood and then to proper information. And this is the most simple math behind this whole process. So you have this initial layers representation, we call the node attribute, and then in each layer, once you transform into the hidden space, and you will average the neighborhood the previous layer embedding, and then you will fuse the information from the message to the graph node representation from previous layer or previous iteration. And then you will apply a nonlinear transformation to generate the current node representation. So if you have any question, please feel free to ask. So yeah, so we can see that key idea here is try to generate a node embedding by aggregating neighborhood information. Two measures here. So one is allow for the parameter sharing in the encoder when we learn the aggregation function. Another one is allow for the inductive learning. So this is basically just a kind of a case study to talk about most the basic concept how graph neurons learn stuff. But in reality, right? So we have been invent a bunch of the algorithm that in the graph neural domain, and each of them, as I mentioned before, have a 4 different types, and each of them have a representative method. I can think about so the big difference between the different method most of the time is about how we design this aggregation function. Okay, so for example, in the graph convolutional network here, we try to using a graph Laplacian decomposition to do that. And in Chebyshev, we'll try to using kind of Chebyshev polynomial to approximate the graph decomposition or eigen decomposition. So in the spatial based method, so messing passing neural network and the graph search, the toil example we talked about before is more likely associated with this spatial based graph filtering. So and then later people invented attention based method that essentially try to capture the different importance of the graph node. And the recurrent based method is a little bit different from all these existing methods. So, but this is the first modern graph neurons paper that essentially try to using a gating algorithm, try to mimic the to encode the sequence of the graph node and to generate a sequence output. So now let's quickly go through this part. So for the graph convolution network, as I mentioned before, so key idea here is try to apply a graph spatial convolution on the graph, so that you have a graph filtering is a multiplication with the signal xi, and then use this eigen decomposition to generate to this computation. However, in reality, eigen decomposition is very expensive, especially when matrix is large and sparse. So later people invent a Chebyshev polynomial trying to accelerate the this computation. However, it's not the computationally efficient later. So people invent first order approximation, just take the first order item and then to do the computation. This is a very rough approximation. However, it's working very well. So this is the foundation of the graph convolutional network. And later people do this renormalization trick, try to stabilize the numerical computation. The GCN have been most widely used graph neurons method have been using for the for example, text classification, question answering, matching, topic modeling, and so on and so forth. So the messing passing network is kind of like try to recast this graph convolution as a messing passing process. So there's two important operations. One is the aggregation function, as we mentioned before, to aggregate the neighborhood information. Another one is update function, is try to update based on the aggregate message and the previous iteration embedding, try to update in order to get a new node representation. However, this is a very generic framework. We can see that it's even considered edge embedding. Okay, even without edge embedding, it can work. Okay, you can just take the node embedding. But the problem is that so with a very large and dense graph, so you may have a lot of the label, right? Even for the first order neighborhood. So this is still very expensive. So graph stage, it take one step further is that, so you don't have to use all the neighborhood. Okay, you just need to sampling or get the fixed number of the neighborhood to save the computation and also to overcome the overfitting. So for the graph attention network, so people found that so all the previous work method, right, that really don't consider the importance of the different graph node. That means that so you don't really consider the contribution of each graph node when we try to generate the aggregate message. So this graph attention network try to dynamically learn these weights or importance. Right, so to basically using the self-attention mechanism that is similar, is borrowed from the transformer. Okay, and then you can do this weighted sum of the node embedding so that you can generate a better node representation. So the getting the graph neural is similar, but it's a bit special in the sense that it's to take into account the edge type and directions. They basically split the incoming, outcoming node so that you can learn them separately. And then when they consider the adjacent matrix, consider this augmented adjacent matrix. And finally, when they do the node embedding fusion, they use a GRU to do the node embedding fusion. So this is quite different from the all previous work. So basically I have been finished for the basic foundation for the DLG for NLP. So next part I'll briefly talk about the graph construction and graph representation learning. So basically for graph construction, we have many different ways to do that, but basically generally considered as a static graph construction and dynamic graph construction. For the graph representation learning, it really depends on what kind of graph type we are talking about. Is it a homogeneous graph or multi-dimensional graph or heterogeneous graph? And later, so let's first talk about the graph construction. So as we mentioned before, the representation power sense, right? Graph definitely will be bigger than sequence will be bigger than background word. So different graph, they have different aspects, and a different graph may capture different aspects of the text. So in generally speaking, that we have a static and dynamic graph construction. So once you have a text, you try to convert it to a graph. And there are so many different ways to construct the graph. So, but in big steps, so we can split them into a static graph and dynamic graph. The static graph, essentially, you can treat them as kind of like pre-processing. Okay, so basically, generally, you have this raw text. You try to generate a graph, and because you see it's a static graph construction, so therefore you just do that one step. And so you basically try to augment the current text with the domain knowledge. So based on the type of the static graph construction, you can think about as many different ways to do that. You can use a syntactic information, you can use semantic information, you can use a topic information, logic information, use similarity between two different graph node, concurrence, node knowledge, and also word knowledge and the application-driven approach to construct a graph. So let's take an example how we're using dependent graph. So for example, if the text input is like there, job, start, elsing, so we can first using a dependence path tree to get the sentence structure information regarding this each of the word token, and then you can add the new edge between any kind of a word token. Okay, so basically here is a two continuous word token and have this bidirectional edge, put them together. Therefore, that you can formulate a new dependence graph. And so compared to the plain text sequence, we can see that there are a lot of the hidden structure information we didn't see before. But with the dependent path tree, we are able to capture that and put that into the current text sequence. Similarly, for the constitution graph, so with a different way to get the different sentence structure information, and then similarly, we can have them together so that we can generate the constitution graph. So for AMA graph, so is a little bit different because AMR syntax is a bit different. So you can think about the text sequence here is like Paul description of himself as a fighter. So here the Paul will be corresponding person. And so it will be a concept node corresponding to Paul. And then you have a describe, you have the name, and you have the name is Paul. And so here there's an argument fighter. So this is a general structure for the AMR path graph. So you have a concept node, and you have each argument node, and also you have this argument age information to help you understand the sentence, the semantic information. And the IE graph, so this is IE graph that's generated. So you can use the OpenIE tool, also using code reference, so that you can put the different like Paul, he, and Roland. All these are referring to the same concept. And this is entity mention, and then you get the triplet, and then you can formulate this IE graph. And this is more concise of the semantic representation of the whole sentence here. So basically you can see that. So with the static graph construction, it's basically try to leverage all existing tools. Okay, like semantic path tree, like constitution tree tool, AMR parser, IE graph parser. You also get this additional information that beyond the current text sequence. But of course, you can also use like a topic modeling approach, try to construct a topic modeling graph. You can also use a SQL graph that SQL graph I have been describing before. You can use it also generate for the similarity, concurrence. All this different way try to construct a static graph construction, so that you can construct a graph that beyond the simple text sequence. But this is not the only way to do graph construction. We can also do dynamic graph construction. For example, you can using input will be raw text, output will be a graph, but the graph construction can be done on the fly together with the graph representation learning. So what does that mean? So assume that we have a bunch of the data point. Data point here you think about as a word or sentence or document. Okay, and when we at the very early slides, I'm talking about the graph edge. So what the graph edge means? It means that there's a relationship between two graph nodes. It also means that similarity between two graph nodes. Therefore, that we can easily cast them as a graph similarity metric learning problem. Try to learning a similarity between two graph nodes, and that will be used as an edge. And once you learn this fully connected weighted graph, so then you can using the graph specification technique to try to pruning this whole graph, because some of the graph edge information maybe it's a spurious, because the similarity score will be maybe very small. In that case, so it should be thrown away, and then you will finally get the learner graph. So, but in order to get the best performance, so if you already have some intrinsic graph structure, right, then you should also use that, because your intrinsic graph structure most of the time will carry important information, although it's not perfect. We will get to this point later. Okay, so for the dynamic construction, generally we have several steps. First of all, you have to do the graph similarity metric learning. Okay, this is one way to construct a graph, the first graph, and then you can using graph specification technique to try to further pruning the graph edge information, and then you can think about for combining the intrinsic graph structure with the implicit graph structure we have learned so far. And we'll also talk about the learning paradigm diagram. So the graph structure learning, first of all, you can custom the similarity metric learning. It's definitely enabled in inductive learning, because you are learning them and the graph the similarity metric instead of learning any specific parameter for each of the graph node. Therefore, that you can choose various of the metric functions that is admitted for compute similarity. So generally speaking, we can combine them into the two categories. The first one is node embedding based similarity metric learning that only consider node information. Other one is a structure aware similarity metric learning is not only about node representation but also the edge information. So let's first take a look at the node embedding based method. So here, pretty straightforward. So we'll just compute the pairwise node similarity in the embedding space. But there are two ways to consider this common metric functions. For example, first one, you can use definitely attention-based method. Other one can use a cosine method. They're all very natural. So the variant one you can think about, it's just using the original feature vectors, and then you have this non-native learnable weight vector to do the hard model multiplication, and then you can do the inner product and then compute the similarity score. Okay, of course you can use a multi-head, right? That's your choice. And the variant one is more like a transformer, right? So you have this lambda weight matrix to transform the original node representation into the new space, and then you do the nonlinear transformation to do the inner product. So the cosine-based method is that we just fix using cosine similarity function. Okay, because cosine is a very natural function to transform any kind of like similarity score between 0 to 1. Okay, and so then you can learn the weight vectors. And so in our paper published in News 2020, so we choosing this use a hard model multiplication instead of using transformer-based type of transformation. It's because that it can just use a vector, so as a learnable weight vector. So this is definitely will save a lot of the parameter size, and also it's more efficient. So we have some comparison to compare using the weight matrix. But anyway, so we can use multi-head similarity score, and then so that to reduce the variance. To compute the similarity score between any of the two graph nodes. So the structure-aware similarity metric is that sometimes you not only have a node similarity information, you can also consider edge information. So if you have edge information, okay. So in that case, it's fairly similar. Just when you consider to compute the similarity, you have to put the edge information into account. For example, you have two different variants to consider that. The first is very straightforward. Right? You just put the edge embedding inside the original one, and then you can put them together to compute the inner product. And the second way that you can independently to treat them and transform that is a transforming matrix, and then you compute as before. If you remember the previous equation that when you compute the node, when compute the similarity and metric function, you just know the representation. So once you get that, so basically we learn a fully connected graph. So but fully connected graph, first of all, is computationally intensive. Second of all is that, as I mentioned, so the edge information may be noisy. So in that case, so you want to enforce a sparsity to learn the optimize graph structure. So there are plenty of ways to do that. You can use NK style of specification. You can use epsilon neighborhood specification, or you can use graph regulation. So the common way, it's very straightforward. Use top K, right? You just choose like top K higher, top K number of the similarity score and keep that for the kind of node. And so this is very straightforward. So the second one, you can choose some kind of a threshold. And once you larger than greater than this threshold, you just keep that similarity score corresponding to that edge, right? Otherwise, just remove that edge. The second one, the third one is try to enforce a graph regularization term. That is basically based on the assumption that any two graph nodes, so if they are connected or if they're close, so they graph representation should be similar. So try to enforce the smoothness between two graph nodes. If it's far away, so then you will get a larger penalty. So of course, right? So many times you may have an intrinsic graph. In that case, so you should consider to combine the intrinsic graph with your implicit graph you have learned so far, because the intrinsic graph typically will carry the rich and useful information. So in that case, you can treat the learned implicit graph as kind of like shift to the intrinsic graph structure, in a way that the intrinsic graph structure is maybe not perfect, but in order to learn the optimize graph structure, you use the delta that you have been learned from the implicit graph. So then you can put them together, use use a parameter to put them together. This is in the extreme case, right? So if you fully trust your original intrinsic graph, the lambda could be 1, right? In that sense, that you don't use any implicit graph structure, okay, information. But if your input graph is completely noisy, right? You don't trust any bit of them. In that case, you just put lambda as 0, right? So then you will purely rely on your intrinsic graph. But in reality, right, you can put trade-off. You can learn a parameter of this lambda as a hyperparameter. So no, okay, you want to learn that. So this is iterative learning that we have been proposed before. So once you have a node feature in the initial graph structure, but this is optional. You can, first to learn a graph structure, and then once you put the learn graph structure to the GM, you will learn a better node representation. And then once you have a better node representation, you will go back, send it back to the graph learner. You want to learn a better graph structure. So you can see that this is an iterative process. Try to automating to learn a better graph learner and graph neural nets. And in that sense, so when do we stop, right? The criteria is very simple. So criteria is that, so once the difference between two learner implicit graph structure in two consecutive steps becomes smaller and smaller. Once it's smaller to the certain threshold, you think about they already converge. In that sense, that you already learned the optimal graph structure. So that is the time that you should stop the algorithm. So for the dynamic graph structures, this is summary. So we have been, use a different technique, to do the dynamic graph construction, and this is a whole, overall picture about the different techniques that you should consider here. And briefly mention the static and dynamic graph construction, the advantage and disadvantages. So the static graph dynamic construction, it's very important to the NLP domain, especially for the domain scientists, because that it gives you a lot of the interesting information. So that is domain information you have. That means that you will have a better explanation once you learn the graph structure. So this is a very nice feature. Okay, but the downside of the static graph construction is that it's maybe not toward to your best. It's not maybe best for your downstream task, because for example the dependent path tree you are using is not really toward to the downstream task. Okay, even though it's already provides some useful information. So it's a suboptimal. And also maybe it's error prone, right? Because the kind of pathway is not perfect. And also, you don't really consider how to jointly to learn the graph structure and the representation learning. But that's also that is essentially the merits of the dynamic construction. You don't need any domain expertise. Okay, you just need to using this learning framework to jointly learn the graph structure and the representation learning. But the downside of that is that you lack of the scalability, because when you learn the graph structure, you have to learn the pairwise. Of course, we have some way to deal with that, but there's some issue there. The second part is that it's a lack of the explainability, because everything is done in the latent space. So therefore, it's really hard to interpret that. Okay, so but of course, it gives a lot of the new topic in this domain. Okay, so once you have a graph at hand, so let's say we have to consider graph representation learning. So this is basically depends on what kind of graph type we consider here. So we have a Hessian graph, we have a multi-relational graph. If you have only one node type but multiple edge type. We also have a heterogeneous graph, right? That means that you have multiple type of the node and also multiple type of the edge. So this is basically kind of like a decision tree that when you should use a different graph neural nets. So basically, once you have graph, right, first to judge is a homogeneous graph or not. If yes, go to use an indirect graph or not, and then can choose the plan GCN plan graph neural nets method to use that. But if it's not, you can also use bidirectional graph representation to learn a better representation. So this is all these are provided by our library. But if the answer is no, then basically it's not a homogeneous graph. Then you should have two ways to consider. One is just to ignore this edge type. Then you can use a Levy graph to transform back to the homogeneous graph. Okay. But the other sense that if it's you want to use a more advanced graph neural nets, so then you can use consider if it's a multi-dimensional graph, then you use a multi-dimensional graph neural nets, and if not, you use a homogeneous graph neural nets. And now I just will very briefly to introduce a different type of the graph neural nets. So well, for the homogeneous graph neural nets, right? So we have been talking about a lot, right? When we talk about the different type of graph neural nets, you can use all these popular graph neural nets to do the encoding for the homogeneous graph. And so for homogeneous graph, so one way that I mentioned before is that so you may not have a homogeneous graph. In that sense, that so you just need to convert like H into as a new node, so that once you do this Levy graph function, So you will have all the graph node, right? And only have a connectivity information. And in that sense, you can use any plan graph neural nets to do that. But how about for the multi-dimensional graph neural nets? So in that sense, so you have to consider how to learn the relation-specific transformation parameter, and also how to include the edge embedding, because right now you are consider the different edge type. So in that sense, so the typical one way to do that is like, first you try to aggregate the representation, right? But this is common graph neural nets. You try to aggregate the node information, right, as a message. In the relational graph neural nets, you are not only consider the common graph node, right? You should divide it into the type. So then you first aggregate the node based on the type, and then you aggregate all the messages of the different types, and along the type wise, you also do the summation, so that you can put them all together to formulate your final node representation. So there are two ways to consider that. One way is that to divide it simply to include edge embedding into the message parsing. So other way is that you also update your edge embedding so that you can have the most updated node embedding and then to compute the final node representation. Both of them have been used in the literature. So how about the Hessian graph? So when we have a Hessian graph, right? So most of the time, so it's like this, right? You will consider using metapaths based way to learn the representation, because in a Hessian graph, right, you have a very complicated relationship. You have a multiple relationship in terms of edge, in terms of node, right? In that case, so the metapaths become very important, because metapaths can really easy to capture the different type of the node and the different type of the edge information. And then you can just try to aggregate the information along the metapaths. You want to do this simple neighborhood aggregation. So, but the learning, in terms of learning, wise, it's very similar. So previously we are learning through the neighborhood. Now we are learning from the type-specific node transformation, and then you just aggregate the information along the metapaths instead to along the first order neighborhood, right? And once you get the representation for each of the metapaths, then finally you do the metapath level aggregation, and then you generate to get the final representation for this graph node. Okay, so I just briefly finished the graph representation learning. So there are a lot of literature. I cover very fast. I know that, but this is essentially a 3-hour tutorial. So you have to compress to the 1 hour. So we have to throw away something. But you are encouraged to take a look at our tutorial later, and also have a recorded video if you want to know more details about each of the graph representation learning algorithm. Okay, so later, so Yu will cover this graph NLP library, and Ban will cover a bunch of the applications using deep learning on graph. So I will leave them to them. And now I will briefly talk about the future direction of this deep learning graph for NLP. So as I mentioned, so graph construction is very important for NLP. So dynamic graph construction, although we have been considering this, but still in the literature is very unexplored. But we think it's very important, right? So because still you don't really to consider the domain knowledge, therefore that you have a big advantage here. But how to effectively combine the static graph construction and dynamic construction, how to effectively to construct, for example, Hessian dynamic graph, and how to make this scalable, is very important. And also for the, you have to consider, right, when you have a logic graph, many people rather consider unit graph, right? How to scaling the graph units to a logic graph is also a very important topic. And people have been talking about transformer a lot, right? Transformer to do the pre-training. So how can we combine these both, right? So essentially, conceptually, transformer can be seen as to learn a fully connected graph as a self-attention. But in reality, the learning paradigm is quite different. So they have their own merit, because graph neural nets is more generic in the sense that it doesn't really assume how they get graph. It just assumes that you have graph information. So in that sense, so they can be combined to each other. So how to effectively combine the advantage of both? And also, people have been doing a lot for pre-training for transformer for NLP, but can we do the pre-training for GN, for NLP and will? especially that, for example, if you have some like structured knowledge, right, like knowledge graph, then in that sense, a transform cannot take a knowledge graph as input, right? But transform only takes the text sequence as the input. So in that sense, that probably you should consider graph neurons to do the pre-training. And also, okay, then basically this is the conclusion. So, deep learning graph is a very fast-growing area today, and very important. That's because that. So I really think that so it can combine the domain knowledge and the power of deep learning at the same time. But there are two important questions you should ask. So first of all, how to convert text sequence into a best graph. Second of all is that how to determine the proper graph from learning technique in order to solve the problem. And here you have a dedicated website, DLG from NLP. So there's many learning resources that you can take a look. And this is our survey paper. It's about in the very long paper. It's about 127 pages, but it's a first comprehensive survey. Try to survey the whole area. And also we have a library, graph for NLP, and I encourage everyone to try and give us a feedback. And that's all. Thank you.
Thank you, Dr. Wu, for your very excellent and dense presentation. So it's a lot of material to take in, but we have time maybe for one question because we're running a little long. So if you have a question, simply use the raise hand tool in Teams, and then the floor will be yours, and you could ask your question to Dr. Wu. If you want, you can ask the question in the chat as well. So if there are no questions, what I'm going to do is ask a single question, Doctor. So it's a lot of material to take in, but one question I have on the construction of implicit graphs is how do you deal with the combinatorial explosion that you have when you have to compare each node to everyone else in the graph? How do you deal with that kind of computational load?
Yeah, this is a great question. So basically, this is one of the few situations that I'm talking about here is about scalability. So currently, it's in most of the NLP domain. So for example, right, when we talk about like implicit graph construction, we are talking about, for example, for a sentence or maybe a paragraph, right? So you typically treat like each of the word token as a graph node. So in this graph, it's not that big. You see a sentence only like length maybe less than 20, right? A paragraph maybe less than 100. So in that case, even though you do compute each pair of the graph similarity, it's not a big deal because so small, right? But the real problem is that so if you try to do this for a really long sequence, so then really you may have this problem. And this is the first dimension. The second dimension is that so if you have a lot of this instance, for example, millions of them, then you have a lot of trouble. So that is another dimension. But luckily that so people have been exploring this. So previously we have been proposed using like sampling-based method. So the key idea is that so you don't really have to consider any pairs of the graph node, but instead you are choosing a few of the representative graph node, and using each of the graph node to compare to this representative graph node, and compute the feature vector, and use that feature vector to represent to use later to compute the similarity score, and that's what will make this construction much scalable. So previously the complexity, computational complexity will be quadratic complexity in terms of the number of the graph node, but with this approach, you can reduce that to the linear complexity in terms of graph node. I think this is a very promising direction to further explore.
Great. Thank you so much, Doctor.
Thank you.
So after this great presentation, we will move on now to the second one from Bang Liu, who's assistant professor at RALI and Mila in University of Montreal, who's going to present graph representation and learning for hot events tracking and user interests modeling. So as I said, Professor Liu is assistant professor in the Department of Computer Science and Operations Research. So that's the DIRO at the University of Montreal and Mila, Quebec. He's a renowned scientist, having published 25 papers at least in top conferences. His innovations have been deployed in real-world applications like WeChat, serving more than 1 billion daily active users. So, Professor Liu, you can share your screen if you want.
Okay, thank you, Fabrizio. So now I share my screen. Let me check. Give me one moment. Actually, I haven't shared with Teams.
But if this is your first time to share, maybe how to change your private setting and quit this meeting and rejoin your meeting again.
Let me check. I think. Can you see my desk?
Oh yes, that's enough.
Yes.
Okay. But I cannot move. Oh, okay. So now can you see my slides?
Perfect.
Okay, thank you. Okay, thanks Fabrizio for your introduction, and hello everyone. So today I will talk about graph representation and learning for hot events tracking and user interest modeling. So basically, I will mainly talk about 2 different kinds of applications. So one is about like how to mining fine-grained hot events from article streams, and another is about how to extract user fine-grained user interests. For example, the hot event phrases or concept phrases from news articles and user queries. So let's start from the first one, which is called Story Forest, with a system for hot event discovery and tracking. So nowadays we are experiencing information explosion. So there are many news media producing different articles or messages. So it's not an easy task to quickly glean what you want to see from a huge amount of information. So traditionally, if you want to know something, basically you input a query in the search engine, and you will be returned a document list, which is like a list of news articles reporting what you're interested in. So basically, in this list of documents, you will receive like very fine-grained articles, and each articles may talking about the similar events. And in this way, because these articles are reported by different news media, they will convey redundant information. And they're not structured, which means if you have like 5 or 10 news articles, you didn't know the relationship between the contents. So what we want to do is like try to aggregate the similar information involving around the same event into one fine-grained event cluster. And we try to organize the relationship between different events. So here shows an intuitive example. So this is about a story which is like the president election between like Trump and Hillary. So in I think it's 1916, 2016. So here basically each green node is about an event, which means a cluster of news articles talking about the same event. And the edges indicates the time or relationship, as well as the content relationship between them. So for example, the node 1 is about like the Trump become presidential candidates. And the last is Trump is elected as president. And there are different branches. For example, from node 3, 4, 5, 6 is about Hillary's health reports. And 7, 12, 13 is about the 3 television debates, and from 14 to 15 and 18 is about the mail door. So you can see that by group the articles about the same event into a node, and by organizing these different events, related events, into a tree-structured story, which we call story tree here, we can track the hot events and as well as like reduce the redundancy by this fine-grained grouping. So this shows the overall framework of the story forest system. So from the first part, which is prepared data, basically we have like a stream of input documents along with the timeline. And then we perform document filtering and word segmentation for Chinese news articles. And then we extract keywords from these documents. And based on the co-occurrence relationship, for example, a pair of words co-occurrence in more than like 4 articles, we can connect an edge between them. In this way, we have a large keyword graph. And then the key problem here is like how we can cluster fine-grained news articles, basically, which means we will have clusters for each hot event. Then in each cluster, all the documents are talking about the same event. So what we did is we proposed the event X 2-layer graph-based clustering algorithm. So the first layer is like we have this keyword graph, then we perform community detection over it so that a large-scale keyword graph will be divided into several keyword communities. Then we can assign each news article to one of the keyword community by calculating the similarity between keyword community and the document. In this way, we have the first layer clustering. Then we can similarly, we consider each document within each keyword community as a node. Then we calculate the relationship between each 2 articles, which says like whether these 2 articles are talking about the same event or not. In this way, we have a document graph for each keyword community. Then we perform community detection again to divide the document graph into subgraphs. Then each document subgraph represents an event. And finally, we have a module for growing stories. Basically, it means that assume we have several existing story tree. Then we have like new event nodes from the event clustering procedure. Then we will decide whether each node belongs to one of the tree or it belongs to a new story. Then we initialize a new story tree based on this event. So for details, you can refer to the paper. So here, this is an early example, which is like initial application for the story forest system. So it's applied to the Tencent QQ browser hot topic list. So it's in Chinese, but basically it is a application. So for each hour, you will have a list of hot events. Then for each hot event in the list, if you click on it, you will have a cluster of documents talking about the same event. So here, this example is about the event, Hawking Public with PhD diseases, back to several years ago. And this is some application scenario for the story. So these are 2 different applications. One is called Zhihu, which is like a Chinese version of Quora, and another is WeChat, the event line. So basically, in these applications, they have like organized the related events into by timeline. So basically, they exploit the line structure because it's easier to track and to visualize. So in this system, a key research problem is like how we can decide the relationship between 2 long documents. So basically, it's a text matching problem. And for text matching, previous research mainly focused on like short sentence matching or like information retrieval, which you have like one short query and one long document. But there is limited research on how to match in 2 long articles. So there are several difficulties for long document matching. One is like a long document is hard to encode. And the second is if you change for example, the passage order in a document, actually it doesn't influence its content a lot. but the embedding of the document may change dramatically. And finally, the time complexity. So if the number of words in a document is n, usually the matching complexity is n squared. So with the increase of n, the time complexity is huge. So basically, our strategy for matching two long articles is divide and conquer. So first, we will divide a long document into several parts. So in this way, if we have two documents to compare with, you will divide them. And the second is you will align each subcomponent of each document so that you will have corresponding short paths to be aligned with. And finally, you can perform distributed merging. So here shows how we decompose a document. This is a toy example about a document. So it only contains like 6 sentences. So what we propose is called concept interaction graph to decompose the content of a document. So in the first step, we will extract keywords from the document. So here it indicates by the red font. Basically, here we just use the named entity as the keyword. And the second is we will group keywords by the relationship, just similar with like what we did in the story forest. You can perform some community section, or you can use other ways to class the keywords. And then you can assign each sentence to different keyword communities based on their correlation. And also, finally, you will connect these different sentence groups. So in this way, the key idea is you use the keyword as the hubs to divide the sentences. Then each document is divided into several groups of sentences. And if you have like a pair of documents, the idea is similar, but is like you will construct the keyword community with 2 articles. And for each keyword community, you will have like 2 lists of sentences from document A or document B. So with such kind of document representation, we can compare 2 articles in the following procedure. So the step A, construct concept interaction graph, CIG, is what we have introduced just now. And then after this step, you will have a document graph. For each node, it's actually governed by like a cluster of keywords, and you have 2 lists of sentences from document A and document B. And then you perform local matching in the step B, which means for each node, you concatenate the sentences in the 2 sentence list, and you perform local matching because it is only a part of the 2 documents. It's comparable to short sentence matching. So here we can apply different measure. For example, we can exploit the Siamese network, or we can extract some features. And after step B, we will have a graph where each node contains a local matching vector. So basically, it indicates the local matching result for each subcontent. And then we can aggregate the matching result over different nodes by graph convolutional network to get a final global matching vector. And we classify the relationship between document A and B based on this global matching. And all these components are trained end-to-end. So we performed like the experiments for long document matching over 2 long document matching datasets, which is the CNSE and CNSS, which is called Chinese news, same event dataset or same story dataset. And the goal is to decide whether 2 news articles are talking about the same event or same story. So we have like 2 major results here. So the first, if you all the experiments on the left are results from the baselines, and all the experiments on the right part are our model and our model's variance. So if you compare these method 9 and method 11, we can know that the graph you can greatly improve the performance with the graph representation, because if you compare this SIMNet baseline with the CIG SIM, the main difficulty is the main difference is in the method 11, we divide the content of the articles based on our graph representation, and we use the same matching module. And we can see that this actually improves the accuracy and F1 score by 4%. And if we, and if we like compare this CLIQ sim and the CLIQ sim GCN, so these two variants, the only difference is for the later method, we will aggregate the local matching vector by the graph convolution network. But for the previous method, we only aggregate this local matching vector by like calculate a mean of it. So we can see that with the help of graph neural networks, we can improve the matching result by over 10% of accuracy and F1 score, which means utilizing the relationship between the contents of a document, the relationship between different sentence clusters is very helpful to further improve the matching result. So the next we want to talk about Giant, which is about ontology creation and user interest modeling. So here our key problem is what we want to infer what are users interested in. For example, if a user input a query in the search engine to estimate resonation speech, so what he is interested in. So let's say if you like recommend articles about Tresemme to a user, he may not interested in because he may not interested in like he's not a big fan of Tresemme. He's just interested about this related events. And you can also recommend other articles about Tresemme's resonation speech. But if a user already read 1 or 2 articles about this specific event, and in this way you will recommend repeating information to this user. So this causes the monotonous recommendation issue. So a good recommendation may be like we can recommend articles about Brexit negotiation. So to achieve such kind of performance, we need like 2 components. The first is we need to know that the Brexit negotiation is a user interest in a suitable granularity. And the second is we need to infer the relationship between user interest. So we will need to know that Tresemme's resonation speech, this specific event, is belong to this higher topic, Brexit negotiation. So what do people care about? So we can generally divide them into 2 groups. The first is events. So event is indicates a real-world incident that involves specific persons, organizations, or entities with a certain time or location of occurrence. For example, the Tresemme's resonation speech, or Apple launch, for example, iPhone 13. And another type of interest are concepts. So concepts are a collection of things that share some common attributes. For example, we can consider the car, Honda Civic or Honda Electron. They are both fuel-efficient cars or economic cars. And for Iron Man or Captain America, they are all belong to Marvel heroes or Avengers. So these are different concepts. So in our Sigma paper, we propose a system which creates a web-scale ontology to represent user interests and document topics. So basically, if you have like different user queries and documents, we extract different phrases from them and try to organize them into this ontology. So here we have different nodes in different color. So the black are categories, which is the most high-level category. So they are actually predefined. We have like several thousand categories in 3 layers. So we have, for example, technology, current events, and the subcategories here. And therefore, we have these gray nodes, the concepts, topic, or events. So they are phrases, heterogeneous phrases extracted from web contents. For example, the purple cell phone, pretty cell phones, or cell phone launch, or Brexit negotiation. And we have different relationships between them. So the major relationship is the either relationship. So some specific, for example, the Newman V5, this entity belongs to the concept purple cell phone, and an entity can belong to different concepts. Similarly for the events and the topics. And we also define some other specific relationship. For example, involved relationship means some concepts are involved in some events. And we have the correlated relationship. So if like two entities are mostly mentioned together, which means they have like very close relationship, so we can detect it by this specific relationship. But the main relationship is the user relationship, which forms an ontology here. So this is the framework for the giant system. So start from the user browsing activity, we will have like different such queries. And for each such query, we will have like top n clicked documents. So on the left, so in this way, we will have a large scale search click graph. So basically, this forms a bi-party graph. So we have two groups of nodes. We have a group of nodes for queries and another group for documents. Then we can apply some bi-party graph clustering algorithm to divide this search click graph into a lot of small-scale query document clusters. For each query document cluster, it will contain several highly similar queries and highly similar documents. Then for each cluster, it potentially contains a phrase which can indicate one of the user interest, for example, a concept, an event, or a topic. Then based on a heterogeneous phrase mining algorithm, we can extract these different phrases, which is indicated by different nodes in the ontology. And we can identify the relationship between them. And finally, based on this user attention ontology, we can tag the user interest based on his browsing history, and we can apply it to different downstream applications. For example, the story composition, because we can know the relationship between different events. Or we can perform document tagging, which is based on the content of a document. We can associate different tags to it to indicate its main topic here. And we can perform query conceptualization. For example, if a user input a query about some cell phone, based on the characteristic of the entity, we can infer whether this cell phone means this user is trying to find some good cell phone for old man or not. Then we can infer, like recommend other similar brands, which is like good for old people to use. So here a key research problem is how to mine this heterogeneous phrase from the query and documents. So basically we use the query and document titles. Here shows an example. So let's say we have this query and these three titles from three documents. And what we want to extract is the concept, the Hayao Miyazaki animated film. And we can actually analyze the characteristic of output words. The first is usually the phrases you are interested in will show some patterns within the title of queries, just like how we use hash pattern to extract different things. And they will show up multiple times because it's like very popular kind of concept phrase. So it's kind of a fixed concept in human brain. So we will repeat the similar phrase in different queries and titles. So they will show up multiple times. And the named entity tag or the part of speech tag are very useful feature to classify whether each word belongs to an output phrase or not. And usually there will be a continuous chunk, and sometimes they will contain one or several like stop words within it. And the syntactic dependency between different words are very helpful feature to extract such kind of concepts. So to like we designed this graph structure to try to reveal this kind of features very obviously. So basically, for each unique word within a title or query, we will represent it by the same node in this query concept interaction, query title interaction graph. And then we will include the sequential urge to indicate like two words are adjacent to each other within one of the query or title. And if two nodes are not connected by adjacent the sequence urge, we will connect them by the syntactic dependency urge if they have this kind of syntactic dependency in one of the titles or queries. And finally, for each relationship, we will also add its inverse relationship. And finally, for each query or title, we will have a virtual start of sentence and end of sentence node for each title and query. And based on such kind of graph structure, we can extract phrases from it. So the first step is we need to perform node classification to decide whether each word belongs to the output phrase or not. So we can perform this step by the relational graph convolutional network. And after that, we will remove all the edge dependency, syntactic edge dependency, and only preserve the forward sequential urge. And then we will try to find shortest path, start from the start of sentence node, ends at the EOS node. And this path will traverse each positive node for one time and has a shortest path here. So this is basically the asymmetric traveling salesman's problem, and it can be solved by existing algorithm. So we have introduced how we can extract different phrases as nodes in a taxonomy. And the next problem is how we can add a new term. So basically we will extract different new nodes from the web content, and we will append it to an existing seed taxonomy to expand its scale. So we want to introduce the details. So basically you can find it in the following the web conference paper. So the key idea is the previous research mainly focused on compare the relationship between a candidate parent node A and a query node Q. But in our paper, we propose to compare it in a more contextualized way. So we will not only compare the parent and child, we also compare it with its siblings as well as its ancestors to get a more comprehensive comparison. And also we will introduce the external description about the different terms to like incorporate the semantic information of different nodes rather than just using its textual name. So we applied Giant to different applications. For example, the feed news recommendation. So basically, it aims to summarize the content of different news articles by the concept or event tag. So for example, here we have this news article. See these cars with less than 2L per 100 kilometer fuel consumption and up to 1,000 kilometer recharge mileage. So here we tagged a concept to it, which is called low fuel consumption cars. You can see that the concept can summarize the content of the article, even though this concept is not shown explicitly in the title or in the content. And here are more examples. So you can see the image. So the left one is about the newborn stars in the entertainment. And the second is about the diet food. And the third is about the trend of house price. So in all these examples, the concept is not directly shown in the title or content, but the concept can summarize the content of news articles in a high-level way. And thanks.
Thank you, Bang, for your excellent presentation. As always, we have about 4 minutes for questions. So once again, I invite everyone who has a question for Professor Liu to simply raise their hand using the tool in the upper right corner of Microsoft Teams. If I may, I'd like to start with a question from me, Bang. On slide 26, you presented how queries are analyzed and decorated with various edges, and you rely on part of speech tagging and so on. But what happens for the many queries that are not grammatically well formed, that are in shorthand or not very well written? Does that perturb or upset the process that you've described?
Yeah, this is a very good question. So here we designed this kind of graph representation. So you'll see that actually it's dominated by the sequential edge, which indicates the sequence relationship in the original query or title. If the query doesn't have a very well grammatical structure, then we may didn't have such kind of syntactic dependency within the query, but we can have if the words in the query show up in a title, usually you will have a similar relationship between them. In this way, because we will utilize like one unique node to represent all the same words shown in a query or a title. In this way, the information can be complemented by other phrases.
Okay, I see. I have another question. So basically, for Giant, you use the search click graph to fuel the creation of the ontology, but so that requires a lot of data naturally. What would be your recommendations for our partners and industrial partners in assistance today who do not have access to such a large corpus of data to create their own ontology from documents that are more scarce?
Yeah, I think so basically we use search click graph because we introduce the information from user actions. So if you don't such kind of data, you actually can use by clustering the documents or short queries directly based on whatever data source you have. So in this way, it's just we need to perform like a short text or long document clustering algorithm first. We can group the similar documents or similar queries together. Then we can perform the phrase mining without even the click action in such kind of data.
And do you have an idea of the volume of data that you used? How many queries, for instance?
Our previous experiment is done based on the real data from Tencent. So every day we have more than 100,000 documents.
Okay, I see.
Yeah.
So thank you so much, Bang, for your very clear presentation. Very interesting.
Thank you. And let me out quick this sharing. Yeah, so am I out for sharing?
Thank you. Yes.
Okay.
There is one question in when someone raised his hand.
Oh, sorry.
Yeah. Hi, Bada.
Hi, Bang Liu. Hi, everyone. Thank you so much for your presentation. It was really so interesting. So basically, I'm more interested on the article, event extraction from the articles, and especially for the ones that the long documents. And basically, based on my understanding, so there are articles that contains, a lot of words and sentences, and as you know, there is a lot of diversity in events in the same document.
Yeah.
And they would like to know how did you, face the challenge of defining what is the most important event in each document, and how you sort all those events.
Yeah, this is a very good question. So there are also some reviewers ask about this question. So usually one document may talk about different sub-events into the same document instead of only focus on one. But we can actually infer the major event from its title or abstract, or for example, from its first passage or the first sentence of each passage. So this is how we can actually infer the main event here. And another way is like you can organize the content of the document with a document graph, and you can calculate the importance of different nodes within it. So in this way, we can for example, for each event, you can calculate a weight for it based on the graph structure of the content. In this way, you can select the dominant event in each document.
Okay, thank you so much.
Thank you.
Thank you, Ban. So we will move on to the third presentation now by Hugo Chen, who's a research scientist at Facebook AI, who's going to present Graph for NLP library and a demo. So Hugo Chen is a research scientist at Facebook AI. He's got his PhD degree in computer science from Rensselaer Polytechnic Institute. And his research interests are at the intersection of machine learning and natural language processing. And he's interested obviously in graph neural networks. So Hugo, the floor is yours.
Thanks. Yeah. Hi, everyone. My name's Hugo. Can you see my screen?
Yes, we see it.
Okay. Great. Yeah. Yeah. Great. So I think we can get started. So my name's Hugo. I'm a research scientist at Med AI. So it's my great pleasure to give a presentation here about the Graph for NLP library and the demo. So this library is developed and maintained by the Graph for NLP team. So as for Graph for NLP team, so we are a group of volunteer researchers and developers from different academic and industrial institutes. So yes, Graph for NLP is an easy-to-use library for R&D at the intersection of deep learning on graphs and natural language processing. It provides 4 implementations of state-of-the-art models for data scientists, and also flexible interfaces to build customized models for researchers and developers with whole pipeline support. Graph for NLP has both high running efficiency and a great extensibility. So this library is built upon the DGL library. So DGL is a highly optimized library for deep learning on graphs. It supports major deep learning platforms such as PyTorch, MXNet, and TensorFlow. It also supports CPU, GPU, and cluster-based training. So the Graph for NLP library also provides interface to the Hugging Face transformer models. So this library consists of 4 different layers. As shown in this picture, we have data layer, module layer, model layer, and the application layer. So for the application layer, we have already implemented various NLP applications like text classification, semantic processing, machine translation, and so on. So, so this library has the following key features. So it is easy to use and flexible. It provides a rich variety of learning materials, including coded demos, documentations, tutorials, videos, and the survey. And also it's highly learning efficient, and it has a great extensibility, as we will talk about later. And also we provide a comprehensive collection of NLP applications and as a corresponding code examples to for quick start. So here you can see more details from the DGL for NLP website and the library documentation. So let's first see the data flow of the Graph for NLP library. So given the raw data, we will have a graph construction module, which will convert the raw data to the graph representation. And the graph representation is stored by our built-in graph data structure. And then we will have a graph embedding module, which will learn meaningful node or edge representations from the graph, from the input graph. And then given the updated node embeddings or edge embeddings, we will have a prediction module, which will produce task-dependent outputs. So here's just a like detailed version of the computing flow of the library. So one thing to note is that as for graph construction, users can specify both static graph construction, dynamic graph construction, or we can apply both static and dynamic graph construction. So this is fully configurable. So since Lingfei has already covered those concepts in his talk, so I will not go to the details of that. So also the library supports variance prediction tasks like node link graph prediction, and also sequence generation, tree generation. So we provide some commonly used mechanisms like attention, copy, and coverage mechanisms for the sequence or tree generation. So here just this table shows some benchmarked results of different GNN models on different tasks, which shows that our model achieved good performance on those data sets. And also that also actually indicates that our library can be used to quickly verify some models on some like a commonly used benchmarks. So here's a deep dive of the graph NLP library. So this figure shows the hierarchy of the library. So we have data set, graph data, and also we have a module which covers like graph construction, graph embedding learning, prediction, and also we have high-level models such as graph to sequence, graph to tree, so that users can directly call the high-level model API to build application quickly. So in this talk, I will focus more on the module part. So I will introduce the graph construction, graph embedding, and the prediction modules in great detail. So let's first see the graph construction module. So this module contains two parts. One is the topology construction, and the other is the embedding construction. So the topology construction aims to convert raw data to a graph representation. So here we support both a static graph construction and a dynamic graph construction. For each type of graph construction, we have implemented some commonly used strategy like dependency, graph construction, constituency, IE, like node embedding based, and so on. So for embedding construction, so as we know that like node or edge embedding initialization is very crucial for the overall performance of a GNN-based model. So this embedding construction module aims to learn the initial node or edge embeddings for the input graph before consumed by the subsequent GNN module. So we provide variance building strategies for node or edge embedding initialization. So here I list a few of them. So I can take, for example, like a W2V by STM, for example. So this means we will use pre-trained like word embeddings, for example, the glove embedding or the word to vector embedding to first initialize the tokens in a node. Then we apply a by STM encoder to then conceptualize the representation of the node. And then we can use that to initialize the node embedding. And then we also support bird-based word embeddings by calling the Hugging Face transformer interface. So and in addition, so this embedding construction module supports both single token or multiple token node. So in our graph, a node can contain a single token, but it can also contain like multiple tokens. So our library is quite flexible at handling like both scenarios. Next, let's talk about the graph embedding module. So this module aims to learn meaningful node or edge representations from the input graph and the initialized node or edge embeddings. So we support like common GNN variants such as GCN, GAT, Graph Sage, and GGNN. And in addition, like we support both the undirected version and the bidirectional version of the GNNs. So users can simply specify the direction option when calling the GNN API as shown in this code piece. And also users can set whether to use the edge weight or not during the message parsing of GNN. So now let's move to the prediction module. So we categorize the NLP tasks into two categories as of now. One is the classification task. So as for classification task, we support node level, edge link level, and also graph level prediction tasks. And we also like provide some building pooling strategies like the average pooling or the max pooling, because given the node embeddings, if we want to get the graph level embedding, we needed to apply some pooling mechanism. And the second type of prediction task is the generation task. So as for generation task, we support, as of now, we support the sequence generation and the tree generation. So in the future, we'll be supporting like the graph generation as well. So as mentioned before, like we provide some commonly used mechanism, like the attention copy and coverage mechanisms for the sequence or tree generation. And also we provide a building high-level graph to sequence and a graph to tree APIs. So this is fully like a configure in model out. The users do not need to like bother the details of those implementations. They can just simply specify which kind of graph we want to construct, like which kind of GN we want to utilize, which kind of decoder we want to apply, and then we can the users can like very quickly build such a model. But if advanced users want to like build a customized like a graph-based encoder decoder models, they can also easily do that by based on our building functions. Next, I will talk about a little bit about the data set. So because like we know that NLP has like a bunch of variants like tasks, and different tasks require kind of the different has different patterns in terms of like input data and output data. So that's why we here categorize our low-level datasets APIs to the following categories, which include a text-to-text dataset, text-to-tree dataset, text-to-label dataset, sequence labeling dataset, and also like a double text-to-text dataset. So for example, text-to-text dataset is suitable for tasks where we have text as input and text as output, and a text-to-tree dataset is suitable for tasks where we have text as input and tree structure the output, tree structure output. And a text-to-label dataset is suitable for example, like a text classification tasks. And a sequence labeling dataset is suitable for example, the named entity recognition task. So here, so this code base shows that like we can build a customized data set based on the low-level dataset APIs. For example, we want to build a dataset API for the TREC dataset. Then we can just inherit the text-to-label dataset, and this could be used for text classification application. So I also want to talk a little bit about online inference. So our library provides different inference wrappers to enable online inference deployment very easily. So here we provide inference wrapper for the classification task as well as the generation task. So these wrappers are quite easy to use. It supports like raw data in and a final prediction out. So as we can see from the code snip here, so users only need to provide the configuration, the trainer model, and some other, and also the data set type, like either text to label or text to text. Then we can easily like call this to enable like online inference. Next, I will show like two demos built upon the Graph for NLP library. So the first demo is about the text classification application. So if you want to run this demo, you can just go to this Graph for NLP demo website and follow the get started instructions in the README section to install the library, and then you can directly find the 2 demos here. You can directly run these 2 demos. So I want to go to the demo page. So let me know if you cannot see this demo page. So here's the text classification demo. So in this demo, we use the Graph for NLP library to build a GN-based text classification module, which consists of a graph construction module, graph embedding module, and a prediction module, as we previously mentioned. So back to slides. I want to talk a little bit more detail here. So we can very quickly build a text classification application by calling the graph construction API, the graph embedding API, and the prediction API here. And also, so I will quickly skip those because we already mentioned that how we can call the graph construction API and the graph embedding API and the prediction API. And our next application is the semantic parsing application. So you can also go to the demo page to run that demo here if you install the Graph for NLP library and the Jupyter notebook. So this semantic parsing application aims to generate a logical form from a natural language. So we can regard this as a graph-to-sequence problem, and we can directly call the high-level graph-to-tree API provided by the library to quickly build a demo. So in summary, Graph for NLP is an easy-to-use library for R&D in the deep learning on graphs for NLP field. So here are a bunch of useful resources about the Graph for NLP library and the DLG for NLP field. Thanks for your attention. Is there any question?
Thank you so much for your presentation, your demo, Hugo. Our friends in attendance today will be able to look at the demo by themselves and hopefully download and try the examples that you've mentioned. Are there any questions from the audience today? We have time for maybe 1 or 2 questions. Well, I have one, Hugo. Since you've shown and demoed an API, could you talk a little about performances? Sometimes graphs can get very large. It may not be a single sentence in input. For instance, you can input a large graph of 1,000 or even 10,000 nodes. Could you discuss the limits of graph for NLP regarding the input size?
Yeah, thanks for the question. I think that's a good question. So as I mentioned at the beginning, so our library is built upon the DGL library. And the DGL library is a highly optimized library. I think the limit of our library in terms of handling the graph size, which we can handle, depends on the limit of DGL. And as far as I know, DGL can handle a larger scaled graph. And also it supports multi-GPU, like a class-based training. So, and also like our library is still, the development of our library is still in progress. So in the future, we want to support like a multi-GPU training, like a class-based training better. But in short, like I think the limit of our library is really depends on the limit of DGL, and the DGL is highly scalable and optimized.
I see. And do you have any salient results for graph for NLP where, a scenario where it has been used with excellent results by a company or in a paper? Do you have any winning scenarios for graph for NLP?
Yeah, that's a good question. So as you can see, like from this benchmark table, so this is not an exhaust list of the tasks and the results, but we can see that like our library is able to achieve good performance on those tasks. But one thing to note is that so those are mainly like demo examples. We did not really try very hard to push forward the performance of the models, and also we did not implement the most advanced models, but we did implement some models proposed in recent papers, like for the question generation tasks and also for the semantic parsing tasks. And in the future, we want to implement more like state-of-the-art models proposed in recent papers using our library.
Yes, a good idea. So there are multiple modules and sub-modules in the Graph NLP API that you've shown. So you can call BERT and so on. So my question is, when you train such a system from the beginning, the node embeddings down to the classification or the prediction of nodes and edges, is that a training that is end-to-end?
Yes, end-to-end.
Okay. So you can fine-tune a transformer while you're learning classification or prediction.
Yeah, exactly.
Impressive, very impressive. So if there are no further questions, I think we're going to, oh, I see there's one question from Mathieu Fortier. Mathieu, the floor is yours.
Yeah, thanks, Hugo, for that great presentation. It's really interesting. I think it's a follow-up, actually, my question on top of what Fabrizio you've been asking. Just wondering if there's a typical inference scenario for these models that you're training here with Graph for NLP. It might be covered in the documentation. Obviously, I haven't had the chance to look at it yet, but just wondering what is a typical inference scenario. So how these model gets optimized, and then is there a serving layer, a serving component? Is it out of DGL, or I'm just curious to hear more about that.
Yeah, thanks for the question, but I think I didn't quite get it. Like you mean service layer. So what does that mean?
Yeah, so my question is more, how would you deploy in an inference scenario, right? These types of models that have been trained for by Graph for NLP. So
yeah, I see. Like I think that's a very good question. Are you talking about like employing the trainer model like in production?
yes, correct.
Yeah, I think that's a very good question. So that's something we would like to support in the future. So I mentioned the enabling online inference here, but it's not really about like deploying it in production. I think in order to do that, we should. So one way to do that is because this library currently is based on the PyTorch, but of course we want to support a TensorFlow version as well. But if we talk about PyTorch, I think one thing we should do is like we can torch script the trainer model, and then we can like deploy it in production. I think the pipeline is there, but we haven't like really supported that yet.
Thank you. So I think you've gone in the direction I was hoping for, like torch script. Do you foresee any, like in your mind, is it going to be a pretty smooth process, or you foresee that you know, converting this into torch script and running these optimization might cause specific challenges, because these, I'm assuming these model architecture are quite complex at the end of the day. So
Yeah, I think there could be some challenges, but I think we should definitely consider that, because it's quite important, because if we really want to deploy this in production, And please feel free to contribute to this library. It's an open source library. We welcome all the developers to contribute.
Thank you so much. Definitely interesting.
Thank you, Mathieu, for your question. Thank you so much, Hugo, again. So I think we're going to conclude. We're a bit late. So we thank our three presenters for their very interesting talks about graph neural networks. I thank everyone for attending this meetup. I hope you enjoyed the presentation. Stay tuned for more news about the upcoming meetup, which will take place in January. So not December, January. Once again, a recording of this event will be available on our website, CLIQ-ai.quebec. And I look forward to seeing you all next time. Until then, have a pleasant day. Thank you.
Thank you, everyone.
Thank you.
Thank you.
Have a nice day.
Thanks.